saying Waku is better because, okay, it's recording already. Okay, let's continue. Uh, Share again. So now, so we say that when the target is the same as the computed output, then we don't need to, excuse me, to update your weights because they are good already, especially if you go through all the data points, yeah, and the output is correct. But uh, it rarely happens, especially at the initial stage. So now there will always be, normally there always be an error, and so with this error you can update your weights. Okay, so now this will continue until this error. It's either this error is minimized to a certain threshold that we want to set, or I mean the threshold or the upper limit of or the lower limit of the error, so that beyond that lower limit, then we're okay, we're good to go. Yeah. Or we can also say that if we didn't reach the lower limit, then we reach the maximum iterations, we are also stopping the computation. So those are two stopping criteria that we already familiar with. Is either the maximum number of iterations or the error, that is the lower limit of the error that is already achieved. So that is this is working, especially for perceptron, when the training data is linearly separable, and then also the step size, or this the learning rate, is set to be small value. Normally learning rate will be around zero point 0.1 or 0.05, it's up to 0.01. Okay, so somehow if there's no given value for a learning rate, we can just set it to be zero point 0.1 or zero point 0.5 or 0.05. Okay, so now, to understand the learning unit, let's consider this so that we know this already. The output is equal to, this is how we compute based on the perceptron, the W0 times 1 plus W1x1 plus Wn up to Wnxn. This is the summation that we already seen. And then our W's can be minimized with the squared error. We set the squared error to be this, such that the target value minus the computed value for a data D in the training set of a big D. Okay, this error is squared, and for each data point you sum this, you sum the squared error, and then you take 1/2. Okay, so this is the error term that we want to consider. Now, again, we use gradient descent. Okay. Gradient descent to take to compute for our delta of W here, using terms of the error term. Okay. So this is the error. We take the gradient of the error. So again, it will be based on the W's, because these are the parameters that we are looking at. So the error based on change of W0, error based on change of W1, error based on change of, and so on, based on change of Wn. So now the delta W therefore is assigned to be minus the learning rate and times the gradient of the error. So how do we compute this? Then just substituting, we know that the gradient of the error is partial of V with respect to partial of Wi. Okay, so we continue. We compute. So the partial of the error with respect to the partial of Wi, we just substitute this value. And so we say, we take in, well, these are just constant. We can take this partial inside. And then this, we take the derivative. So this is 2 comes here, and then this one, just copy this one, and then take the derivative of the inside. So take the derivative of this one. So derivative of TD minus OD. Okay, so now we distribute. We know that this is constant. Okay, the target value is constant. This is given by the data. Then this is W times X of the data. Okay, the output we know from the equation here. Output is W times X, the given information, the given data. Okay, so here we just substitute output is equal to W times X of the data. Okay. Now, because this is a function of W, you take Wi, the rest of the W's, W1, 0 up to Wn, will be 0 except for Wi, where this is a function of Wi. And so here, the corresponding X corresponding to Wi is Xi of the data set. So that's why here the Xi of the given data set. Okay, so this is 0, this means negative, and so now this is the partial of E with respect to Wi. So now we are remaining with this one. So we can use this to correct our W. So now if you can see delta W, the W, okay, this is changed in terms of the W, the previous W, delta W will be now based on this one, TD minus OD, the target on the data set minus the object, minus the output of the data, computed output multiplied by negative of XI of the data set. Okay, now XI of the data, this is the one, XI of the data set, target minus output multiplied by the learning rate. Okay, so in the most part, this should be have been this part here will be here. Okay, well, you can also do this by accumulating the previous error, but for the most part, we do this. You update the weights based on this gradient of the error. Okay. So the perceptron training rule guaranteed to succeed if the training examples are linearly separable again, and the learning rate is sufficiently small. And then we use a linear unit training rule we use gradient descent because we say that it's guaranteed to converge to hypothesis with a minimum squared error by setting the minimum squared error for our error term. Then it's given to converge given that you have sufficiently small learning rate n, and then when this is even successful even when there's some noise on the data, and when even when training data is not separable by age. Okay. Okay, well, we will investigate that later. Okay, now, so this one will give you some of the techniques or the tricks that we can use here in neural network. So now we say that there are two modes that we can use. One is of the gradient descent method. One is the batch mode gradient descent method. Batch meaning we use the whole data, the error using the whole data set, the big D. The difference here is that we use the big D and we use the small d. What does it mean? It means that we use the error, okay, the error term based on all the 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 data set, based on all the information from the data set. But here we use the gradient of the error based only on one data set, one value of the data set. Okay. Okay, what does it mean? It means that here, for example, here we take the summation, the big D, the error of the big D, we take the summation for a squared summation of the squared error from D, element of D, throughout all the D's. So for example, if there are four items in the data set, it will be for I is equal to 1 to 4. Yeah. So that means that we use all the information in the data set. But in this case here, the small d, we use only a portion of that. Okay, that means that, for example, we take the error based on the first data, then we take the target value and the computed value only of the first data subset. Okay, not all the information in the data set. Okay, later we can see that we use this. Okay, as we discussed last time in the discussion in support vector machine, we mentioned that the summation was gone. Okay, if you remember. Okay, well, it is the summation, strictly speaking, the summation should be there. Okay, using this batch mode of gradient descent. That one is also computing the gradient descent method. Okay, or you can choose to remove it for simplicity but you have to go through all the data set. Yeah, remove it for one data set, make the correction, and then make the updates of the weights through all the data sets. We will see this later in our example. But for now, okay, just to simplify things, to let us be less confused, we will use this incremental mode and the gradient descent by removing the summation term. Okay. So again, multi-layer neural network or multi-layer perceptron, and then now we consider the sigmoid units, which is a different kind of a decision-making process. Okay, where in this case it's done, it's much more capable of doing things compared to the multi-layer perceptron. So here in this case, it's able to classify these many different data set according to their symbols. Okay, and these symbols can be uh, a function of a certain action. Like for example, here you have inputs of F1 and F2. So F1 here and F2 there, and it results into some action, head, head, or hood. Okay, or I think this is oh, maybe this is a sound. Yeah, this is a sound that I think these are signals. Yeah, that gives you the corresponding word according to that sound. And in this case, neural network is able to classify them. Okay. So for example, if the sound F1, the sound is here, and F2 sound is here, then it must be this particular hood. I don't know where's the hood here. Okay. So this is an example where the multi-layer sigmoid units is able to compute. So what's the difference with the sigmoid unit against the perceptron? Well, we still have the same model of the neuron, where you have this cell that's doing the computation, and you have input parameters connected with these connections, and then the output. Whether in this case you have one output, only one tentacle here, one connection. It could be several outputs as well. So that means several connections to the other neurons. But in this case, you only have one. So now, what's the difference? Here it remains the same, where your inputs multiplied by the weights remains the same. Yeah. But the difference is how you take the output. So in this case here, the output is run into a sigmoid function, is inputted into a sigmoid function. The sigmoid function is this. Graphically, it's like this. So before it's like a step function. Here, the function goes from -1 to 1, like that. So in between, there's this. Yeah, there's this discontinuity. But in the sigmoid function, it's a continuous function. Okay. The nice thing about this is when you take the gradient, and then you can always take the gradient no matter where you are in the graph. Okay. So here can say that the sigmoid function can be represented by this 1 over 1 plus e to the minus x, where x is the input. And the nice thing about this is that the derivative with respect to x will be just exactly that function multiplied by 1 minus the function itself. Okay, this is the derivative. Now this is very much useful for us. It will make our computation a lot easier. Okay. So now let's compute exactly the way we did before. Okay. Now we will still use the partial of the error with respect to Wi as a summation of the squared error. Okay. And now we do the same thing. We repeat. Now, what is the derivative here? Well, we repeat inside. We write this one and take the derivative of this. And now, because this is a constant, so this is minus of the output divided by partial of Wi. Okay. So now this is the output. Okay, this is a chain rule. Okay, we're only concerned about it. Here, we take the negative out. The negative is out here, everything else, and we concentrate on taking the derivative of this. So the output with respect to net of D, we understand that this is already, net is the input to the sigma. And so we already know that this is the output times 1 minus the output. We already did this one. Okay, if this is your function sigma of inside, this is the net, and so the derivative with respect to that net is the sigma, this the output itself, times 1 minus the output. Okay, so we know this already, that net is the input of the sigma, and then now we take the derivative with respect to that input, it's output times 1 minus output. Okay, so what is the partial of the net with respect to wi? Well, again, the net is just the summation. Okay, the summation of, the summation of wi times the x of the data set, which is of course the equivalent to the dot product of the weight vector w multiplied by the x input. Okay, so now this is because the w here is consisting of w0 to wn, and we are only taking the derivative with respect to wi, and so the rest of them will become 0 except for the xi on that particular data set. So what's remaining is the xi of the data set. Okay, so now we substitute. This one remains the same. Okay, and then what was this, which is that we put here, and so the other one we put here. So the two terms, this term comes here, and then this term is here. Okay, so now this is your partial of E with respect to wi. Okay, so it's simple. Okay, it is just about the target value minus the computed value times the computed value 1 minus computed value. That's all. Okay, two terms. Okay, two values plus the data. Plus the other information multiplied by the data of xi. Okay, that is in the data set. Okay, so those three information, you get already the partial of V with respect to wi in order to update your weights. Okay, so now how do we do this? Okay, later we'll show an example, but for now we say here, okay, there are some tricks that other people are using. I want to introduce it to you, but there are ways, or you can develop your own method of computing, but then the terms are the same. It's just that the approach are kind of different to some people. So now we solve for the sigma k. Okay, of course we initialize first. For example, if you want to uh, run the computer neural network, then we initialize the weights first, and then we do this iteratively until we are satisfied with our weights, because we are going to update the weights. Okay, so in the final sense, this is the WIGK, then the WIJ, sorry, WIJ updated with the previous WIJ plus uh, the delta of WIJ, which was what we are looking for. Okay. Okay, now the WIJ is based on this information, where this is the learning rate and delta J is this. So delta J started from here. Okay, delta K, okay, because there are different deltas when you are considering the output, the final output, or in the hidden layer. Okay, so if you are in the final output, this is easy, you can compute this. But when you're in the hidden layer now, this delta K goes in here. The delta K goes in here, multiplied by the W of the output layer, the weights of the output layer, multiplied by this. Now that is the WH of the hidden layer. And then you can just repeat. Okay. Well, we can, okay. There's our easier symbols later here. I created my own symbols for your ease, for your convenience. Now, okay. So for example, if this is our neural network, okay, where I just want to use one hidden layer so that for you to understand exactly what's going on, okay? We know that before in the XOR, we're saying the XOR problem cannot be solved by the perceptron. Well, because there was, and plus there's the absence of the hidden layer. If they don't use the hidden layer, okay, there's no way you can solve the perceptron problem. Now we use the hidden layer. There's no way we can solve the XOR problem. So with the XOR problem, later we'll show that it can be solved using one hidden layer and also the sigmoid model of our neuron. Okay. So what do we do here? So this is what we do. So here we have one output, the overall output. Okay. It has its weights W11 and W12. Okay. This is how you're going to update these weights. Okay. And then here in the hidden layer, your output are Z1 and you cannot see that. Your output are Z1 and Z2. Okay. And the way we update the weights for all these hidden layer weights, we call them Vij. We will use, these are some, I write these symbols because other authors are using them. But in an overall sense, all we need is this: the learning rate times the output times 1 minus the output. Okay. Target minus the output times the output times 1 minus the output. The weights of the hidden layer multiplied by the data point. Okay. So we can use the batch mode or the incremental mode, but for us to avoid complications, we just remove the sigma. Okay. So that means that everything is known here already: target output, output for the k, for whatever k we are using. Okay. And well, there's only one target output here. There's only one output. There's only one target. So this one will be one all the time. I mean, it will be constant. Will be just one parameter. We don't need the summation. Okay, in our case. But if there was several outputs, we'll take the summation, and then the weights will be these weights and the output of xi. Okay, things will become clear if we, and then remember that zi, and z2 are outputs. Okay, outputs of the hidden layer, and we know how outputs are computed. So outputs are computed. Okay, that one maybe is a good information. Outputs are computed based on the sigmoid function. So here, the input of V1, okay, V1, these are the weights V1, and then V2. These are the weights V11. This should be, this is wrong. This should be V21. V12. V10, V11, and V12, because everything goes to Z1. So the vector V1 and their components, the vector V1, V1, V1. So this is the zeroth element, the first element, and the second element. So V1 multiplied by X. Okay, X is X1 times X2. Okay, then X is X1. Okay, X is equal to, sorry, X1, X2. Okay, the same thing as the X here. Okay, and there's a 1 here. So let me correct that. It will be 1, X1, X2. Okay, and then your V1 will be V10, V11, V12. Okay, so 3-element vector multiplied by 3 elements, you get the output Z1. Okay, and then here the same thing. There will be 3 elements vector. So in this case, V2 is equal to V20 and so on, V21 and V22 multiplied by the same X, 3 elements, and then you get the output. Okay, the sigmoid output here, and then here, what is this? Okay, well, this one will be Okay, the input x, in this case, the inputs are z1 and z2. Okay, multiplied by w1. So z1 and z2 plus the bias again. So in this case, x will be 1, z1, z2. Okay, and your w1 will be, of course, the bias. Okay, or your w10, w11, w12. Okay, so I think you're okay already with those symbols. Okay, now let's go to an example so that this one will be all clear to you. Okay, so first, before we go to an example, what we'll do when you're going for back propagation computation of neural network is first is you feed forward. That means from the given input, you will initialize all the weights. All the weights will be randomly initialized. So whatever here, we initialize all the values of these weights. Okay, just some small value, positive or negative, less than 1, positive or negative, doesn't matter. Okay. Now try not to use 0, yeah, because it will, the computation will assign it to be 0, but don't assign the weights to be 0 initially. Okay. So now, I mean, it will be corrected, but it's better not to put them into 0. And so now it will be computed feed forward until you get into the output. Go to the next layer, computed, go to the next layer, compute until you get the output. Okay. So once you get the output, you back propagate. Okay. You compute the output, you correct the weights here, then after that, compute the output here, you correct the weights and so on until all the weights are corrected. Okay. So that's the idea of the back propagation method. Now let's try. Okay. So we'll solve the XOR example. So the XOR example, again, you have the inputs 0, 0, 0, 0, 1, 0, the inputs x1 and x2, okay? And these are the outputs. These are our target values, okay? Those are the T, okay? And what is the output? The output are the ones that are computed, okay? The output of this Z1 of the hidden layer, the output of this hidden layer are computed like this, a sigmoid function, okay? The Z1, the output of that hidden layer is computed by this Z2, okay? Now the output of this output here is computed using Y1, okay? So this is Y1 or output equal to that, okay? So strictly speaking, this should not be X, but we can call it Z, which is equal to 1, Z1, Z2. Okay, I just want to be very, very strict about the symbol. Anyway, but here we know that these are the inputs, Z1 and Z2, plus the bias of 1. Well, here this is the final bias when they compute it, and then it will be our output. So we will compute this update of the weights, of the weights. The W's are here. These are the W's, and the V's are here. Okay. Okay. So that's how we proceed. Okay. So again, we feed forward first, we compute until the output, and then we back propagate and compute, correct our weights. Okay. That's the idea. So we have to initialize our weights in a small random number, and then we assign all these. Do you see it? Yeah. So this is our V10, this 1, input is 1. Here you have input x1, x2, and these are the weights, okay? Here we can initialize our weights, and this is bias 1. And then we can initialize our weights here, and this will be the output, okay? So again, I just continue to compute this one, we will use these equations. Now, so we initialize the weights to some random values. Okay, so the value of V10 is minus 0.3, V11 minus 0.21, and V12 is 0.15. Okay, and V20 is 0.25, V21 0.24, V22 is 0.1. Okay, W10 0.4, W11 minus W10 minus 0.4, W11 minus 0.2, W12 is 0.3. Okay, those are the initial values of our weights. Now we feed forward. Okay, so how do we do when we do feed forward? So here we say we compute. Okay, so from the input you have x1 and x2. In this case, we use the data of 0, 0. Okay, well, you have your data here. You have your data x1 and x2 0, 0 because it is an XOR. So it will be 1. XOR will be 1 if one of the values of the inputs is 1. Okay, if both are 1, then it becomes 0, and both are 0, of course it becomes 0. It will become only 1 if only one of the input is 1. Okay, so let's do that. So now in this case we use the input of x1, x2, 0. Okay, so here this is the equation. Okay, maybe I think okay, this is better. I'll show you both screens. Okay, so we compute feed forward, so we use this value. I pressed the wrong button. I said stop share. How do I go back? Did I stop sharing? I mean, am I still sharing my, hello?
No, sir, I'm not sharing the screen.
Am I still sharing? I think I'm still sharing, yeah? Is my screen still visible to you?
So it's not visible.
Yeah, I think it's still visible. Hello?
So it's not visible.
I cannot hear. Is my screen visible to you?
No, sir, it's not visible.
It's not visible. Okay.
No.
I think I accidentally put stop share. Okay. Okay. Never mind. Share? Okay, there. Share. There's a new share. Okay, there. You can see it now. Can you see my screen now?
Yes, sir, we can see it.
Okay, thank you. Okay, now, so our data is 0, 0, yeah? X1, this case here, you have, let me annotate so that it will be, okay. This is the data set that we are getting now, 0, 0, and the output is 0. Okay, and this is 0, 0. So feed forward, we say we initialize, these are the initial values of our weights. We have V1, V1, okay, this should be V0, V10, V11, and V12. Okay, anyway, it's here. V10, V11, and V12, and then V20, V22, V1, V21, V22, and W10, W1, W11, W12. Okay, all the weights here are initialized to these values. So how do we compute this? So now we compute the output Z1 because we are moving forward from the input here going forward. So what is Z1? To compute for Z1, we compute first this Zn1. Zn1 is that V1, the dot product of V1 times X. What is that? So it is just V11. Okay, well, it is just V10, V11, V12 multiplied by, like that, the bias 1, then X1 and X2. Okay, there you go. So now we know that V10 is 0.3, bias is 1, V11 is 0.21, and then the first input X1 is 0, and then V12 is 0.15, input X2 is 0. Okay, so it results into 0.13. So this is the result of, I mean, point minus 0.3. So that is the, I'm just copying this one corresponds to that one. Okay, so that's this part here, the summation of all the biases and the inputs. Okay, I mean the weights and the inputs. And now you apply the function, apply the sigmoid function into Z1, Z in 1. So now minus Z in 1, 1 over 1 plus e to the minus Z in 1, 1 over 1 plus e to the minus this is 0.3, then it results into Z1, therefore is 0.43, 0.43. Okay, so this is solved. Next, we solve for Z2. Okay, the same thing. Okay, let me lower it a little bit. The same thing, we'll have, again, input V2
Eh?
transpose multiplied. Can you see it? You cannot see it.